Alright, 15.7, the second part. These are integrals that we have to set up in the next chapter, and I need you to get really comfortable with it. Now, you really don't have to follow directions as when it says use spherical coordinates, or if it's specific, you could use whatever you think is best. You know, on a problem like this, you obviously just have to do A, B, and C. But if it says use spherical coordinates, and you feel, you know what, I could probably use cylindrical coordinates, it's fine. The goal is, when I look at this in the next chapter, I have to come up with which of those to use myself. So first, I need to figure out how does this shape look like. Z equal x squared, so plus y squared under a radical. That's really a cone. So that's something like this. Oops. And above by a paraboloid, so you're running something like this. Like an ice cream cone, so to speak. There we go. So it depends on how you're looking at this. So if I want to set up, let's see, set up a triple integral. Now in this case, they specified cylindrical coordinates. Alright, well, if I look at the triple integrals, in part A, I'm running dz, so I know that z runs from bottom and exits out of the top, and that's going to be dz. So r d theta, well, the shadow on the floor, if I look at this, the shadow on the floor is going to look like a circle. If you look at how these intersect, if I look at this from the top to the bottom, it looks like a circle. And the circle is actually square root of x squared plus y squared equal 2 minus x squared minus y squared. So that is, let me think really quick. Is there a faster way of figuring this out? So I could say r equal 2 minus r squared. And I could say r squared plus r minus 2 equal to 0. So r plus 2, r minus 1 equal to 0. R equal negative 2, that's not in the first quadrant. R equal 1. So that's a circle with a radius of 1. So that tells me 0 to 2 pi and 0 to 1. Of course, you could really convert those if you wish. B, I'm looking in the direction of r. In the direction of r, so if I write the triple integral, well, that's going to be a problem, because r is going to run, it's going to run from the origin, and it's going to terminate on r, on z, r equals z, and r d theta. Oops, I'm so used to that. dz d theta in this case. Well, theta runs from 0 to 2 pi, and z is 0 to 1. And I need another double integral, plus r dr dz d theta. Now, theta is 0 to 2 pi regardless, but now, if I'm going to run from z equal 1 to z equal 2, I have r running from 0 to 2 minus r squared. And part C, if I'm running in terms of theta, that's, well, theta is going to run from 0 to 2 pi regardless, because it's going to run all around. R dz dr, well, theta is going to run 0 to, then z is going to run from r to 2 minus r squared. Z runs from the bottom to the top, and r will run from 0 to 1. Okay, just double checking everything. Seems, yeah, that's fine. Oh, except for that one. I messed up. When you say dr, you can't have an r, you have one r equal. So when I took z equal 2 minus x squared minus y squared, that's z equal 2 minus r squared. When you say dr, that's r equal. R squared equal 2 minus z. So r equal the square root of 2 minus z. There. So on this homework, I just needed to set up the integrals. You really don't have to work out anything. Here they give us graphs, and we want to play with those a bit. And here it's your choice, even though it says dz, r, dr, d theta. You could use whatever you like. I don't mind. So when you look at this, you're going to say, well, set up an integral evaluating the triple integral of what? Well, in this case, do you see it's best to run from z equals 0? And here they're trying to really get you started with this, and they kind of manipulate the problems to match, which is fine. And when I say r dr d theta, all what you need now is to be really comfortable with these graphs. R equal 3, the cosine of theta, is a circle wrapped around the positive x-axis with a diameter of 3. So if you really want to run this, you're going to say theta is going to run from negative pi over 2 to pi over 2, and r runs from 0 to radical 3. I'm sorry, to 3, it's not a circle centered at the origin, to 3 the cosine of theta. And that would be it. So again, do the 3D first. Once you run in one direction, and here they want us to run it in the z. It's best if you see it that way because we're so used to x and y, but things are going to change slightly. How about here? The triple integrals. And I'm going to run again, it seems, from the floor, and I'm going to exit out of z equal 3 minus y. That is dz r dr d theta. And if you look at how this works, I am running, again, you should get really comfortable with this. You really don't need this graph. I see r equal cosine of theta is a circle with a diameter of 1 wrapped around the positive x-axis, and r equal 2 is twice that circle. So again, if you glance at this, you'll notice it's hollow on the inside. So you're really running from negative pi over 2 to pi over 2 again, but now you'll notice r is running from the inner and terminating on twice the cosine of theta. And that's pretty much it. You really don't have to work this out again. I just needed to set up those. The ones you're confident with, that's very good. If not, just ask and we'll work this out in class. And how about this problem? Again, if I had my choice, I would use rectangular on this. I wouldn't use polar, right? But still, triple integrals, and you should be able to do them in all different ways. dz, well, z runs from the floor and exits out of 2 minus x r dr d theta. They want it in that term. If it was me and I said find the volume, I would really probably set it up in terms of rectangular. Y equal x. And y equal x and y equal 1. And they're talking about this region. Well, let's see how this works. If I'm going to run d theta, theta is going to run from pi over 4 to pi over 2. And r is going to run from 0. And if I say y equal 1, isn't that r the sine of theta equal 1? Doesn't that mean r equal 1 over the sine of theta? Or r equal cosecant of theta? And there it is. That do the trick. Again, rectangular would have been a lot nicer, and that's why you really should get comfortable with this, because it's going to be your choice on the long run. Here we're making sure that you are being able to use certain coordinates when needed, but on the long run you're going to be deciding. So here I want part A, find the spherical coordinates. Well, if it's a sphere, now evaluating the integral in spherical coordinates is a lot of work. But setting up the integral is really, really simpler than the traditional. So what was that? Let me check. Okay, it was rho squared the sine of phi, d rho, d phi, d theta. Well, obviously we circle all around. I run from the z-axis and I terminate on the xy plane, and it seems all over this region I'm running from rho equal 1 to rho equal 1 plus cosine of phi. So working out the integral is a lot of integrating, evaluating the integral is a lot of work, but to set up the integral it's really simple, and I'm after setup more than anything in these cases. How about this problem? The solid bounded by the xy plane, again rho squared sine of phi, d rho, d phi, d theta. Well, obviously this runs all around, right? And let's see. It says bounded below by the xy, so we're going to run to below. We're going to run to pi over 2 because that's on the xy plane. On the sides by rho equal 2, okay, and above by the cone. So it's going to run all the way to this cone, phi equal pi over 3. I think I got it backwards. Let me check. I did get it backwards. And the reason for that, phi starts at right there. It's going to really start at pi over 3, and it's going to terminate at pi over 2. There we go. And rho is going to run simply from 0 to 2. Again, the goal here is for you to get comfortable with all of these different shapes, because when the time comes you have to make this call. And here's a problem that you should spend enough time on. Let D be the region in the first octant. That's very important. Bounded below by the cone. Bounded below by the cone. Okay, below. So the cone runs only in quadrant 1. And above by a sphere, there. So like a quarter of an ice cream cone. Express this using cylindrical coordinates. If I want to use cylindrical coordinates, I'm gonna run dz first, Z is going to run from the cone. Z is going to run from the cone. The cone's equation is really Z equals square root of x squared plus y squared. Since I'm going to go for RD theta, instead of writing this, I'll simply write R. And it's going to exit out of Z equal 3. No, take that back. I'm sorry. It's going to exit out of, this is x squared plus y squared plus z squared equal a 9. So z equal the square root of 9 minus x squared minus y squared, or simply the square root of 9 minus r squared. And it seems theta is going to run from 0 to pi over 2. We're only going to terminate on the first quadrant. And r is going to run, think really quick. If I look at where those intersect, where do these intersect? If I take this and I throw it in there, let's see. I'm looking at z actually right there. I'm looking at x squared plus y squared plus, if I square this, I'll get x squared plus y squared equal a 9. So I'll get 2 into x squared plus y squared equal a 9. So r squared equal 9 halves, r equal 3 over radical 2. So 0 to 3 over radical 2. Again, you could take this shadow on the floor and you could draw the 2 dimensions if you really want. And it really looks like this, in which this is 3 over radical 2. No need to rationalize. And if I go for B, they want us to use spherical coordinates. Well, rho squared sine of phi d rho d phi d theta. Let's see. Well, theta runs from 0 to pi over 2. That's quadrant 1 only. Phi runs from 0 and it terminates on pi over 4. And phi runs from 0 to 3. And again, that takes care of it. Let me just see if I need another video for this. Nope, we could do it here. Alright, find the volume. Again, it's up to you how you do this. I'm going to take the volume to be. Now, if I'm setting up the integral, well, you see a sphere, use spherical coordinates. Here I see a sphere and a cone. I'm going to run by dz, r dr d theta. Z runs from negative the square root of 1 minus r squared. And it terminates out of z equal 1 minus r. That's very simple. And I already see, they already labeled this for me. It's a circle, 0 to 2 pi, and r equals 0 to 1. Now, they use symmetry a lot in those, and it helps a lot, really. So they would go, 1/4 of that, and they multiply it by 4, but you really don't have to do any of that. And if I look at the next problem on the list, here, if I was picking, if I had a choice, well, I do have a choice. Again, you're going to have to make this call. It's up to you. How do you do this? It makes no difference. I should have shrunk the other one. That's okay. So here, volume is going to be triple integral, and I'm going to run again dz, r dr d theta. It seems z runs from the floor and exits out of, that's going to be r. And the circle, by now, if you notice, this is on the negative x. If you're not sure, you're running really from pi. It's a circle. Okay, oops, on the negative x-axis. It's running from pi over 2 to 3 pi over 2. and this is running from 0 to negative 3, the cosine of theta. And again, that takes care of business. And if I look at the last portion, again, the same deal. I'm looking at the triple integral. Z is going to run from 0 and exit out of 3 the square root of 1 minus r squared dz r dr d theta. And now I'm looking at a circle wrapped around the positive x-axis. So that's going to run from 0 to pi, and it's going to run from 0 to the cosine of theta. And that's pretty much it.